today's set of notes are about the combined and ideal gas laws. We've spent a lot of time in the last few days learning about different gas laws and how to deal with them mathematically. And so today we get to learn about two special gas laws that kind of put everything together. There is a set of notes for you in Schoology if you want to print those out and use those or along with this video. And if you do, there's your topic and data as you need to. All right, so if we put it together. So if we think about Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, and that's a lot of different math relationships to remember. And we can simplify it using two equations that put them all together, the combined gas law and the ideal gas law. So the combined gas law is something we use when multiple things are changing. When we have a change in temperature and the number of particles and the volume, etc. All right, and so when we use the combined gas law, we use it when multiple things are changing. The only thing we assume is constant is the number of moles of substances. So if you kind of look at our equations here, oftentimes we could go ahead and we could write Boyle's law, putting these both over 1, and that would work as well. But you'll notice that in all of our equations, the P's are always on the top, the V's are always on the top, and the T's are always on the bottom, which means you can combine them. We can combine Boyle's law, Charles' law, and Gay-Lussac's law all together to come up with P1 V1 over T1 equals P2 V2 over T2. All right? And that then is something that we can use to solve any of our equations. So let me show you how this works. Okay, a 3-liter gas sample at 20 Celsius and a pressure of 1.2 atmospheres is allowed to expand to a volume of 8 liters and 0.75 atmospheres. Okay, so we've got the pressure changing. We also have the volume changing. Okay, so more than one thing is changing. And when more than one thing is changing, we go ahead then and we say that's the time to use the combined gas law. So here I go. We're going to go P1 V1 over T1 equals P2 V2 over T2. All right, so let's go ahead and let's start filling that in. So do we know the first pressure? Yes, we do. It's 1.20 atm. Do we know the first volume? Yes, we do. It's 3.50 liters. Do we know the first temperature? Yes, it's 20 degrees Celsius, but we remember we have to change that into Kelvin by adding 273, which gives us 293 Kelvin. All right, then that is equal to our new pressure. Oh, do we have pressure? We do. It's 0.750 atmospheres. And then we have a new volume. Okay, yep, we know what that is too. That's 8.00 liters. Do we know the new temperature? No, they're asking us for that. Final temperature, so that's T2. Okay, so just like we did with other equations like this, we are going to solve this by cross-multiplying and dividing. So I'm going to go ahead and we are going to say 1.20 atmospheres times 3.50 liters times T2 equals 0.750 atmospheres and 8.00 liters times 293 Kelvin. All right, so now to go ahead and solve this for T2, we need to get T2 by itself. So the way we do that is by dividing everything else away from it. So 1.2 atmospheres, 3.50 liters. That's going to cancel it on this side. If I do it on one side, though, I have to do that on the other. So 1.20 atmospheres times 3.50 liters. Okay, this, if I run that whole thing through my calculator, 0.750 times 8 times 293 divided by 1.2 divided by 3.5, I get a final answer of 480 18.6 Kelvin. All right, so that's combined gas law. The second gas law that we have today is ideal gas law. And the ideal gas law is a situation that we use when nothing is changing. In other words, the conditions at just one point in time. And the equation for the ideal gas law is PV equals nRT, where P is the pressure in either atmospheres or kilopascals. V is the volume, got to be in liters. N is the number of moles. T is the temperature in Kelvin, and then there's this R, and this is the gas constant. It's just a number, it never changes, and it will have one of two values. If the pressure is in atmospheres, we're going to use the number 0.08206. If the pressure is in kilopascals, we're going to use the number 8.314. So what would an ideal gas law problem look like? It would say, at what temperature will 0.654 moles of neon gas occupy 12.30 liters at 197 kilopascals? All right, so if I look in this problem, the first thing is I know that it's ideal gas law because nothing is changing. They give me 1 moles, 1 liters, 1 kilopascals. Nothing is changing. So I'm going to go ahead, then I'm going to say this is definitely ideal gas law, and we're going to use PV equals nRT. Okay, so do I know the things in here? Do I know the pressure? Yes, I do. It's 197 kilopascals. Okay. Do I know the volume? I do. It's 12.30 liters. Do I know the number of moles? I do. It's 0.654 moles. Do I know the value of R? I do. In this particular case, our pressure was in kilopascals. So that tells me that I'm supposed to use that number, 8.314, for that constant. And last but not least, we have the temperature. Do we know the temperature? No. There's the question they're asking us. At what temperature? All right, so now we've got this set up, and now I just have to solve for T. So once again, to solve for T, I need to get rid of the other things that are with it. So 0.654 moles, 8.314, cancels. But if I do it on one side, got to do it on the other. 0.654 moles, 8.314. Okay, so now I have a temperature that equals 1.97 times 12.30 divided by 0.654 divided by 8.314, which gives me a temperature of 445.6 Kelvin. And there's my answer. Let's do one more that's a little bit more complex. It says, determine the value occupied by 2.34 grams of carbon dioxide at STP. Hold on, what's that? We've not seen that before. What is STP? Well, STP is a set of conditions. So standard temperature and pressure is what STP stands for. Standard temperature is 0 degrees Celsius or 273 Kelvin. And again, that's the number we'll use because we're dealing with gases. And standard pressure is 1 atmosphere. So if something tells us that it's at STP, we can know that it is 273 K and 1 atmosphere. So let's go back to our problem. It says, determine the volume occupied by 2.34 grams of carbon dioxide at STP. And again, we know that that's 273 K and it is 1 atmosphere. Okay, so they've given us a grams, they've given us a temperature, they've given us a pressure. Nothing is changing. Since nothing is changing, that means this has to be the ideal gas law. Okay, so PV equals nRT. Do we know the pressure? Yes, we do. It's 1 atmosphere. Do we know the volume? No, we don't. That's what they're asking us for. V. Do we know the number of moles? No, we don't. Okay, so let's leave that as N for right now. And the next one they've got here is R. And in this case, we're using atmospheres. And so R is going to be 0.08206 And we've got, do we know the temperature? Yes, we do. We know 273 K. Now we got a problem here because both volume and N, number of moles, are not known, and we need to have a number for one of the two of them. So is there any other information we have? Yes, there is. 2.34 grams of carbon dioxide, right? And we know from work we've been doing all year long that if I have grams of something, I can change that into moles by using the molar mass. So let's figure out the molar mass of carbon dioxide. Carbon dioxide is CO2. So that's one carbon, which if we look at the periodic table, has a mass of 12.01 grams. And it's two oxygens. Each oxygen on the periodic table is 16 grams. So altogether, that's 32. So this particular thing has a molar mass of 44 grams per mole. Okay, so the last part here is in order to figure out change moles or grams to mole, we're going to go ahead and we're going to start our problem. 2.34 grams times 44.01 grams 1 mole. Grams cancel. I'm left with moles. That is what I want for an answer. Put that into my handy dandy calculator, and I get 0.053 moles. All right, so I can go ahead and I can put that in here, okay? So this becomes 1 ATM times V equals 0.053 moles times 0.08206 times 273 K, okay? So in order to solve this, I divide both sides by 1 ATM to get that V by itself. And so V equals 0.053 times 0.08206 times 273 divided by 1. And you end up with a volume of 1.19 liters. That's it. Okay, so now you know how to deal with combined gas law and ideal gas law. And so you can go ahead and work some problems doing that. Thanks.